to start with Professor Yara do Amaral Coutinho. She is a physicist currently affiliated with the University Federal of Rio de Janeiro, the European Organization of Nuclear Research, the University of São Paulo, and member of the Atlas collaboration. She has experience in the field of physics, particularly in elementary particle physics and fields. She'll talk about the jet physics lecture with emphasis on Large Hadron Collider experiments.
Okay, please. Thank you, the organization. Thank you, Farinaldo, Gabrielas. It's all okay. Let's start with it's an overview of the jets, the study of jets, the current study of jets. Let's talk about the beyond the standard model signatures. That's the main point of this workshop. So at this moment, LHC has been exploring standard model. It's very important to study standard model. Signatures, and also perhaps beyond the standard model contributions. So we are going in a high luminosity project. We are in a shutdown at this moment. So we will deliver more data to be analyzed. LHC has a large physics program, mainly about the measurements of the standard model parameters with high precision. Okay, so until now we have a nice agreement between standard model predictions and experimental results. Okay, let's see. I don't remember to put here, but we have nice plot the modified couplings against mass, and then we see the mass of the quarks B, C, top. And then this prediction is very important too, because after the Higgs discovery, okay? But it's also important to increase the detector sensitivity, okay? To be prepared for the search of a new physics, okay? The targets is ongoing studies of known process, standard model, mixed with the beyond the standard model predictions, okay, the models, and in a way to search new phenomena, okay. Of course, the discrepancies among the measured and the predicted parameters can be a test of the standard model and also to indicate a possible beyond the standard model contribution. Sorry. Here's I think it's very important to see the timeline of the LHC and Atlas. Its point is here, yeah. So we are in this period to be prepared for high luminosity program, colliding protons at 14 TeV energy of center of mass energy, and this is timeline of Atlas. Okay, it's a little bit shifted, but it's the same timeline. Okay, this picture is a little bit boring because okay, see Atlas, but it's very important because we are I'm going to talk about jets, and we have to understand the subsystem of the detector. It's not all detector. There are a lot of not by 5 subsystems: the inner detector, the calorimeter, the muon spectrometer, the solenoids, and so on. And I cannot see here, but the trigger and the data acquisition systems. Okay. So for the high luminosity program, we have upgrading all subsystems, electronics, the calorimeters, liquid arc anti-alcohol. We have a new detector. It's concerning about the time the determination. Is very precise, and also in the data acquisition trigger. Okay, we increase the rate, the output rate now will be 10 kilohertz. Okay, it's a technical information. So it's important to do the performance analysis. We have to call the trigger. I don't know if I have, okay, it's not here. The trigger. What's the trigger? It's a filtering system. Selects the physics that you need to analyze it. Okay, we have some rates. The first one is hardware trigger. So we reduce this megahertz to kilohertz, and the great majority of the collisions are rejected, the output. So let's move to the second level trigger software, and then the event rate is 1,000 events per second, okay? So the data accepted by the trigger system are saved. For example, I would like to study TT bar production. So the trigger gives me all the cuts dedicated to TT bar analysis, okay? It's different, for example, for analysis concerning muons, so on. So it's important to select the data because there is a huge, for example, first you have to produce the Monte Carlo for that analysis, containing the model information, and you receive the data. Both, they have the same trigger information for TT bar, concerning the TT bar analysis, okay? So you select, so you shrink the data, because the data, the samples are huge, okay? It's impossible to work with a huge, large events or recorded events. So collisions at LHC, you know, it's simplification of the proton. It can be proton or antiproton-proton. There are some interaction among the constituents, the partons. And then after this, you have production, for example, is the W going to jets here. And this interaction is going to the many changes, decays, emissions of glues and so on. It's a very rich environment to study, very complex, okay? So this is I think it's very interesting picture about the interaction, the levels of it. We have the initial states, there are protons. In this case, we have the interaction among the constituents, the partons, okay? From this side here is U, and to describe these objects, we have the PDF, parton distribution functions. You have math here, okay? So we have the hard collision. Hard collision, is among the constituents, and then the hard process generates the output here. It's a Higgs going tau, it's a final state, and also can produce parton that suffer hadronization, and the final states here, kaons, pions, and so on. So the final states are taus and kaons, pions, etc. So the final state, from the initial state to final state, we have a lot of activity. Here I put here, here it's underlying event. It's not the events that are not produced occurs using through the hard process. It's here, okay? You have to take into account this. So jets, let's begin. So there is a definition, it's a collimated spray of particles, stable particles, arising from the fragmentation hadronization process of a parton after a collision, okay? They are produced, we have a large production of jets at LHC, okay? So we are, the main subjects are the hard scattering, okay? And then also we need to define in terms of energy deposited in the calorimeters, cells, okay, you have to reconstruct the energy, and identify the jets by a jet algorithm. Normally NKT and Cambridge Arran. I don't know if I have the here. So this is a nice picture. You have a proton-proton, the interaction point. You produce in partons. You can say this is a parton jet level. After we have the particle jet that connect track jet, the information of moment, position, with the calorimeter jet is energy. After this, we have the jet, energy, and so on, okay? So we have different types and definitions. Normally, you know QCD jets. They are produced by the strong interaction. We have also jets produced by hadronic decay of boosted particles. They are massive particles like W, Z, and Higgs. They have a large moment, and the final states are boosted constituents that we collect in a jet, okay? Photon jets and electron jets, they are unusual features. Photon jets and electron jets, normally we have the single photon, production of single photon, but if you have, for example, a Higgs or a ALP decay into 2 photons, if they are boosted, you see 1 photon, not 2 photons. So we call this photon jet, okay? It's a very interesting feature. And for each type, we have to apply a different calibration, okay? There is a sequential steps, a little bit boring. I don't know if I have the, no, sorry, here. So we have the, here, jet tagging. It's important, we identify the particle that originated the jet. It's a parent jet, okay? We have a standard approach, but also we can apply techniques, boosted decision tree, etc., to increase the efficiency of the identification. And the jet reconstruction algorithms, they capture all the products of the jet to build the jet with the final. This picture is very interesting. This is a collision, okay? The collision event, proton-proton. This is the interaction point. This curvature is the calorimeter, the part of the atlas, for example, and this is the phi and eta plane, and the production, the particle production, the jets and so on, going through this surface and deposit some information. Here is the jet reconstruction, okay? You see some points here associated to the jet. I applied the jet algorithm here and identify some energy deposits and so on. What's this? What is this? This objects? They come from a Higgs, a W, a Z, or a T. Okay, so this is the role of jet tagging. Okay, the tag puts a label. Okay. Yeah.
So, hello. There are some advanced techniques like DNN and CNN. They are neural network algorithms. But for example, a neural network algorithm uses, they learn the usual behavior, and after it, they identify something new using the same structure as before. So how can you search for new physics using an algorithm like that, like a black box that learn how it is the general configuration, but how can you predict new physics with this?
Yeah, good question. Okay, you have to compare with the physics from the standard model, okay? The final states. You have to see the many variables that you have, for example, distribution, PT distribution. You use all the time PT distribution, invariant mass distribution, energy distribution, eta phi distribution. You have to compare with everything that you know before, okay? So it's important to increase the precision of the measurements, okay? To see if we have a different behavior. But in all analysis, in a set time, we put a blind view because you cannot have a bias. Then you do everything, then you remove this to see if there is a difference, okay? So it's an important question, but you have to use the previous knowledge about particle physics, okay? But you use all the distribution. These techniques, it's an advanced techniques, but uses some distributions, the usual energy, momentum, and so on, okay? It's not different. But you have to pay attention, okay? You can see a bump, okay? Let's see if this bump is really a message from the standard model, beyond the standard model figures. Perhaps not, okay? It's fluctuation. So you have to pay attention. It's, okay, you have a large bump. Let's see, okay? But use the known distributions, cinematic distributions, okay? You see a Z prime, okay, Z prime has a bump here in this mass. So you analyze first Z, the physics of Z, and then you, but it's not, we have to be careful about the new physics, okay? So, oh, it's new physics, no. Normally, no.
Can I make a comment?
Yes, yeah. Of course.
So I think the new physics, it's a little bit more on our phenomenological side than on the hands of those algorithms with neural networks. So we need to analyze the models and what we would predict we want to see to propose new searches. So I don't know, 10 years ago, no one was talking about displaced vertices, for example, or forward facilities. Then there were many proposals of models with dark sectors, with actions that had those proposals that we would see it maybe hundreds of meters forward, maybe some meters forward. And now we have more analysis on those topics. I think that's how we usually do things. So I think what Yara was saying, that's how we, the neural network here is used to reconstruct the data to do the analysis. However, I did heard about some groups that would use deep learning to find things we're not expecting for. I don't know how those things work. They are very complicated algorithms, but it is harder because we have too much data. So it's really hard to look for something you don't see, you don't expect to see.
Yeah, and normally when you use these techniques, is to improve the efficiency, to identify something, okay? It's not new physics. You have to understand the usual physics, the standard model physics. Then, okay? But they are very useful, of course, for standard model and beyond the standard model, okay? So the tag is an important, I have some pictures, very interesting pics about the analysis using the machine learning techniques. Here, okay, it's how the jet reconstruction algorithms they works. Okay, they are seed is the topocluster in Atlas. To build a jet, you have the deposition in the cells. There is a strange picture. This is the input to use the reconstruction algorithms. Okay, normally they use the information of distance and moment, transverse moment. Okay, we can analyze small air jets. It is a parameter in the plane phi eta. Okay. So normally use it to light jets associated to quarks and gluon, and large jets, big or fat jets, to reconstruct hadronically decaying massive particles. Okay, there are a large fraction of the calorimeter with the energy deposition, and there are also all other techniques like Brugum and so on. Okay, so with the jet. What's the steps? The clustering, it's a clustering process. So you match the energy deposited in the calorimeter with the track or ID in the inner detector with the particles forming the jet. And we measure their properties for momentum, okay, and so on. So the jet, this picture, this object, the algorithm, they should be free of diversions, QCD, collinear, okay, infrared, when they have a small energy, very small energy. So the hard jets, they are not affected by the small angle, collinear, and soft splittings, okay, that appears in the parton shower. So the results must be finite and at every order of in perturbation theory. It's detailed about the jet algorithms. Okay, so let's talk about the Anderson model using jet. So we have here the boosted resonance. They are very interesting. We have a heavy particle beyond the standard model particle, very heavy, 1 TeV of mass something, is produced in the proton-proton collision. It goes to standard model or even beyond the standard model particle, I, with a high PT, okay? So this particle decay into, can hadronically decay, and the final states are closed in a jet, okay? As this particle here has mass, the X has a greater mass than Y, they are boosted. They are producing a boosted regime, high PT, then we cluster the final products in a jet, in a cone, more or less, okay? Let's go. Let's move it to, let's say. So the advanced techniques, of course, they are associated with machine learning, okay? We have the flavor tagging. We have to see, we have to separate B and C jets from light jets, okay? Because light jets in general, for analysis using B or C and Higgs going into BB bar, light jets are a QCD background. You have to disentangle this type of jets, okay? The separation of QCD jets from jets clustering from boosted massive particles, W decay, Z decay, Higgs decay. And an interesting study is about the inside the jet. What is there is inside the jet, okay? So this technique is, we call them jet substructure variables. And then we apply this to increase this kind of study to obtain nice results, okay? Okay, let's move it. It's a very interesting, this is a chain Z prime to TT bar, T to W and B. I am interested on the final states of the W, two jets. two quarks. Okay, two quarks, they are represented by two jets. This is the opening between the two final quarks coming from the W. Its approximation is proportional to the mass of W and the PT of W. Okay? If you increase the PT, the opening goes to small angles. Okay? Okay? So it's like a boosted regime. Okay? And then you have, in this case, you use a small air jet, not a big air jet. Okay? So here you see the opening for this simulation, okay? And the PT of W, we begin with 100 more or less, and then going to 800. We see here, it's important that we are analyzing this final states here. It's the key two quarks coming from W. You see that the products, we have a density here, the products of the W are less collimated. You see the parameter is equal 1. Okay? So you analyze, depending on the W, the PT of W, which parameter you have to put your jet. It's a big jet. So W. It's a change. We are analyzing the W. W. You see the boson, okay? I put this formula, but it's the mass of W, PT of W, okay? It's let's see. But of course, if W is beyond standard model resonance, you have this for W, but for a beyond the standard model resonance, what's the regime, the distribution? Okay, you have a parameter to compare. Okay, but for boosted, if the PT, the WPT is high, it's a high PT, of course, the final products, they are collimated, okay? It's not beyond the standard model. It's for standard model, beyond standard model, for standard model resonance W, boson W, okay? So, we have here, it's a very new paper about production of a pair of two tops, okay? And then the technique use machine learning, deep learning techniques, okay? But the focus is top and met, for Farinaldo, top, charm, and met. So it's interesting to tag these quarks. Okay, you have to confirm that they are top, charm, okay? And what is missing is the new physics, okay? So we have matic in the imbalance, okay? It's associated to these invisible particles, can be a candidate for dark matter, okay? And this analysis is important to tag it because the rest is a met, okay? It's another analysis using bottom. Why bottom is very important? Because the Higgs, the coupling with bottoms is the highest among the particles. But bottom is special because long lifetime, secondary vertex, okay? And we have the decay into muon and neutrino. So we have less activity in the detector. Okay, you see the picture. I did it. Two protons producing big jets here, and light jets. So they made the improvement. Boosted was they present a regression algorithm in Boost 2024. In this technique, I think is regression, is based in machine learning, okay, in order to calibrate the jets. okay? But the focus is big jets, okay? So the regression improve the estimation of the PT of the big jets, okay, as compared to the standard calibration methods, okay? So this new algorithm will be efficient to perform a search of new particles decaying to big jets, okay? Let's see. The scenario is, I put the same information here, but the picture, the next picture is very interesting, okay? It's a simulation of Atlas. We have 3 levels here. Truth, sorry, Gabriela, but truth is the particle is produced in Monte Carlo without the Giant. Giant 4. We have the production, a nice production. So it's the highest peaks here. They applied the study 13 TV, anti-KT 1.0, some inputs here. The PT between 400 and 1,500 GeV. The invariant mass is between 40 GeV and 300 GeV. We have a region of resonance here, okay? Here is the, I don't know, here we have the first Z into BB bar. So this is the truth, the ideal. We have the usual here, nominal calibration, and the regression. Regression gains against the nominal. It's important not the peak will have a difference because they are truth, but here the shape of the peak, okay? The width of the resonance. The next is the Higgs, okay? Now the new regression results, okay? It's better than the nominal, and for the T, QQ, and B. This is the 3 resonance. So with this method, we increase the performance and also see the shape. It's very important, the shape, the width of the peaks, okay? With the new technique. So the final, not the final, slide, but now let's see inside the jets. So use techniques considering jet substructure, okay? So they help to distinguish different origin of the jets, discriminating separation. Sorry. The most important here, the background, Kissidig background, okay? So if you improve the B-jet identification and so on, see the QCD background. If there is new physics, perhaps here, okay? But you can, we are sure that you can separate distinguish the background, the QCD background, okay? So these techniques, we have also origin of the jets, the separation signal background, okay? Or perhaps probe new physics. Hello. So we have 2, there are more, Lungjet plane, okay? I think it's more robust. It's a phase space of all emission described by 2 variables, transverse momentum and the angle of any given emission with respect to the emitter. You take your jet and you remove all the emissions, okay? You separate them. It's a representation of the internal structure of the jets, okay? It works well in association with machine learning. And subject variable, it's a measure the number of energetic subjects inside the jet, okay? And it works well with machine learning techniques. So to build the Lungjet plane, you have some technicians, okay, variables. This is a jet. It is emissions, okay? You take this information, the first is the core of the jet, first emission, you take the angle and the PT. The second, the same, and so on, okay? You have the angle between the emission, the plane rapidity and phi. You have the PT, momentum, transverse momentum, okay? And this is a fraction of moments of each emission. You iterate this, going back to the hard branch and take the next emission, and so on, okay? Normally, the Lund jet plane is defined as the density of emissions in a plane is angle and transverse moment. This is a representation of the moment. This is a jet with two emissions. Here you have the moment, transverse moment, angle. You see each emission has a transverse moment angle. Small angle here, okay, at this side here, this projection here, you have a jet with emission and emission a secondary jet, okay, a secondary emission is represented by points. You put in this plane transverse moment and opening of each emission of the jet. It's a collection. Okay. So this is important. It's a way we have the jet, the core, and the emissions. Okay, you take the opening and the fraction of the moment. This is the Lund jet plane for QCD jets. Okay, you have a region with wide angle, hard collinear, and so on. And Lund jet plane was built for QCD. Okay, jets. Okay, a picture of dijets, QCD jets at the left side. This is Lund jet plane representation, and the right side a boosted, a W jets produced in the decay of W. Okay, you see, this is a scale. Of course, this is the great majority of the jets are in this region. You see band, yellow band here, yellow band, green, green, blue, blue. Okay, but a great concentration of jets, they have this range of KT and a wide angles here. It's 1 over delta. Delta is the opening. When you produce a W, when the boosted final states, you see a mess in this picture. You stop the red band is destroyed completely, and you have here a region very special. Okay, when you go to this in the Lund jet plane diagonal, they represent the mass of the particle. Okay, I put in here. Okay, I did the calculation and this region, you see there is a concentration of jets. The red, they are going here, okay, the green, yellow, and blue, but it's a mess. There is here, okay, you don't have a strong blue here, okay, jets with this properties, they disappear from there, and we'll disconnect this green, red band. So this is a origin. This is a, I know that the jets in this plane come from a W decay, okay? This is the difference. So the next is subjetness. You see how many subjets we have inside the jet. It's good for top decay, because top decay is 3 jets. You have 3 subjets. This is the formula associated to the subjetness. The idea is this. This is a big jet. You have the jet direction and the subjet direction, okay? And the constituents. So, boosted hadronic W decay against boosted dijet QCD. This is a W, okay, two quarks, two jets. So, jet direction here and subjet direction. The boundary of the jet is was built with R equal 0.6. Okay, we can distinguish the direction of the jet. When you go to the boosted dijet QCD, see, it's QCD jet, quark and gluons. You have a shower here, and then it's difficult to see. Let's see the jet direction. It's a spread of the products of the jet. Okay, this is the subjet direction. So we can put in two variables. We see W jets, QCD jets. You don't see a big difference between them. But if we plot in a plane, tau 1, tau 2, okay, we see a difference. This picture is interesting. Here we can say that the W, the subjet from the W, they are very close to the direction of the jet. For the QCD jet, we have a spread of the direction, okay? It's a way to distinguish boosted hadronic decay of bosons and QCD jet. Okay? Finally, I think is the last analysis using subjetness. So it's important because you see single photon against photon jets and QCD jet. Photon jet is an unusual object to analyze. ZPP, Higgs to X, gamma gamma, two photon jets, okay, and QCD jets. You analyze the three process. Now you use the usual, conventional variables, substructure variables. For example, hadronic energy fraction, the energy that was deposited in hadronic calorimeter, okay, and the number of charged particles in the jet. Of course, we need to see the photon in the final state. They cannot convert in a pair of electron and positron. And the QCD jet has they have charged particles, for example, pions and so on. And we put here the variables associated to the subjetness framework, okay? We train the BDT with conventional and the substructure variables. Here, all the set, conventional and the substructure, this final. So let's see the results, okay? We have photons, 2 photon jets and 4 photon jets also, and QCD jets. We have we cannot take care about the many curves here, but here, -1 from the BDT, the output is background, 1 signal, okay? So the substructure, the new one, and the conventional, okay? See, photons and 2 photon jets. Photon jets, there is a part here in this place of the plot, but you can see they present the same output response. So in this case, you cannot distinguish photon jets from single jets. single photons, photon jets from single photons. Okay, in this vertical response. The horizontal response is the response from the substructure variables. Okay, you can distinguish here. It's like it's more to signal and background. And here the QCD presents in the middle. Okay, there is a contribution from QCD jets in this analysis, of course, but it's not equal one, the response, okay? But we can separate, okay, the conventional separates the photon jets from QCD jets. When you go to the four photon jets, we put more photon jets, we have, we can distinguish, they have the same response, but we can distinguish photons from 4 photon jets. Here we have some deposition and the QCD jets, okay? So this technique is very useful to distinguish different types of jets. So conclusions, flavor tagging, the techniques works well to discriminate B and C jets from light jets, from QCD jets. In this, I did not mention, but we have to combine the B taggers. For example, the low level is secondary vertex, impact parameters, and so on. You feed the deep learning classifier, okay? It's you mix, and then with this we increase the performance to distinguish. The proposition of variables like subjectness offers a direct measure on how well the jet energy is aligned into subjects. Okay, excellent to explore for boosted object identification. Any subject associated with machine learning techniques promote, in the case of single photon, photon jets and background, we have a weak identification between photon jets and single photon, but a strong separation concerning the QCD jets, okay? And subjectness also distinguish busted objects from W hadronic decay from the jet QCD. And finally, Lungjet plane. I mentioned some time ago with Bertrand and discussed a lot, was not used yet to study EM showers. Photon jets, okay? We have to build a Lungjet plane for EM showers. I think it's an excellent opportunity. Going deeper in jet substructure associated to machine learning techniques can be successful in the future beyond the standard model search, okay? But until now, you have to work well with standard model, okay? That's all, okay?
We would like to thank you again.
Oh, thank you.
Professor Yara Coutinho. It's open. And
1 minute. 1 minute.
thank you again. And you'd like to open now to questions?
Thank you very much, Yara, for your presentation. So I have a question about your last slide. I saw that all these results are from 2013, right? So what about now?
Ah, yes, yes.
12 years after it. Is it possible to separate between photons and two photon jets?
Yeah.
Or this technology had not improved during this period?
I think it's from the, imagine it's not new for us at this moment, BDT and so on, but in 2013, the people are using this, okay? And then if it worked at this moment, of course, I didn't have time to see the upgrade of this analysis, okay? But I think it's a nice paper, this. I have
how they separate these photons between photons and two photons exactly? But at least as an outsider, I can see
I'm also
just a light.
No. So, see, you have to, it's good to compare the output of the BDT. Okay, and then the idea you put only the conventional. The conventional, you can see there is a separation. Here, signal is close to one background. Okay, but there is some interference here among between photons and two photon jets. It's not clear because single and two are very close. I don't know, of course, we have some approximation, in some formula, but we have to, I think, I don't know, but it's very difficult. We are working with Bertin, but it's, imagine it, it's one or two. There is a transition region, okay? But the idea is to improve the identification of one, the single and double. Single and photon jet, okay? It's not easy. In this, okay, I don't know if we have at this moment an improvement of this analysis, but here you can put, okay, we have some probability, okay, this guy here is a photon, single photon, I have 4 photon jets, but you have to increase the number of photon jets to separate. But from in this, okay, all the time QCD jet is background. I think it's very important here, okay? QCD jet are background for photon jets and single photons. Okay.
Yara, I'm sorry, but do you use also the time synchronization to define the number of photons?
Sorry?
Are you using here in this analysis the time synchronization to define the two photon jets, 4 jets, 1, 2?
Yes, yes.
And what is the resolution, do you know, of the time resolution that you can check on that?
No. Okay. No, I don't know.
Because it's very fast, so I'd like to know that. Okay.
But for me, it's very clear that we know the background. Okay? Because there is no contamination of background here, red here, no. So we know the backgrounds. But photon jets, we have to be
I see.
more.
So it's a clear separation between QCD and electroweak.
Yes, the most important.
Okay.
Okay?
Anyone have questions?
There's a question there in
Hi, Yara.
Hi.
Nice
Hi,
to
Pires.
see you.
Nice to see you.
You are very good.
Yes.
Very young. Yara, I saw in the last transparency that you in the end you say this is a very sophisticated technique, right?
Yeah.
I have no idea. It's not my area. But in the end, you say you can use this to look for new physics. And when I heard new physics, I got very excited. What kind of new physics can you look
Dark
for?
matter candidate, for example, if you see the ALP, action-like particle decay into 2 photons, boosted 2 photons or 1 single photon. If you can see the difference between them, you can analyze these 2 candidates of dark matter decay, then you have signal new physics, okay?
Any kind of dark matter?
No, it depends on the final state. You have to see the final states. 2 photons, okay, ALP, decaying 2 photons, okay?
So, yeah, so for instance, just taking the leap on what Carlos said. So we propose, as Yara was saying, we propose to Atlas collaboration to search for vector dark matter that does couples to photons. So you have 2 dark matter species and 1 photon. So there's like a trilinear coupling between 3 vectors. And then if the mass splitting between the two dark matter particles are small, and then so it's kind of very similar. So it mimics of two photons, but it's not two photons, it's one dark matter and the other one. So that's what we are doing now, and we are using machine learning to do so. So whenever you have a photon defined state, then you need to make sure whether you have one photon or two photons, and that can be applied to new physics or to whatever.
I would like to mention, I think it's more important as the final state photon. Photon and electron, they are called the E-gamma objects. So the liquid argon, the calorimeter, has a high precision to identify electrons and photons. Yes. Both are showers, electromagnetic showers, but photon doesn't have a charge. So you understand, you identify with a high precision electrons and photons. So to do a nice analysis, use photons and electrons. Okay? Sorry. Hello.
Hello. Okay, thank you for your talk. So I have a very naive and general question. Can you talk for B-jets coming from displaced vertices? So imagine you have a neutral particle that then decay. Huh?
See, here.
Yeah, so that's my question. Is this possible, or
It's possible. Sorry.
if you are saying that you can identify B-jets, right? So I'm thinking of a B-jets coming from a displaced vertex. So for instance, you can imagine a light neutralino that then decay not from the interaction point and decay to a B-jet through our, in our parity violation scenarios, you have these kind of signatures. So that's my question. Is that possible, or?
It's possible. It's possible because we are working with ALP, and the ALP, there is a decay length. So the direction of two photons, they are not from the direction, the initial interaction here. You have to take into account this. This is the same with a B-jet. Okay? Very special. You have a lifetime. It's not large, but lifetime. You can follow the B-jet. So this variable, secondary vertex impact parameter, they enter in the BDT, for example, and you identify the B.
And can you identify the charge of the B-jet as well?
The charge.
Charge.
Yes.
Yeah.
Yes.
So you can know if.
Yes. You collect the final states, of course, the B, but yes.
Yeah. And then the efficiency. How does the efficiency?
The B is heavy. It's not a light. So in some sense, this is the same with photon jets and single from background. You have the background from light jets, and behavior is completely different.
You can see that at least for the three lightest quarks, they are MeV particles. The B is heavy, and it's the dominant channel of the Higgs decay.
Yeah.
So B quark is very dominant on these types of and it is the lightest of the heaviest quarks. So it's predominantly produced B and C. Tops are not.
No, they don't have.
So B tagging, for example, is essential to the discovery of the Higgs boson. Without it, you cannot say for sure with more than 6 sigma that the Higgs exists.
Yeah, but I imagine if it's come from a displaced vertex, it's more complicated, right? Because you have the B that also has a lifetime, right? But also comes from a displaced vertex. So
you can see that displaced vertex And this displacement
It's-
exactly is the time, the lifetime of the beam
Yeah.
on the lab frame. It's very interesting. And usually they tag the Higgs because of this displacement.
Yeah.
Yeah, but what I'm thinking is a neutral particle. That's
I see.
But the Higgs discovered was using gamma-gamma channel. Because gamma, you know gamma. Because they are produced in electromagnetic calorimeter. You have 100 not so to take this particle because it's an E-gamma object. Okay, so the calorimeter, electromagnetic calorimeter, is the precision calorimeter. Okay, the jets, the showers, they are not big like the hadronic QCD showers. So the important at this moment is a signal against QCD background, and QCD background comes from light quarks. Okay.
okay. Good, thank you.
Oh, thank you.
Thank you. So we can continue talking in the coffee break. They are waiting for us, and we turn back. Thank you.